Welcome. Let me say something more about Dehn-Sommerville spaces. I've worked on this for many years, and there are many different connections between different parts of mathematics. So first of all, everything is in a finite abstract simplicial complex. We have here a unit sphere, notion of unit sphere, which is the boundary of the smallest open sets which you have in that space. And now we can define a Q manifold, or Dehn-Sommerville Q manifold, as a simplicial complex such that every unit sphere is a smaller dimensional Dehn-Sommerville sphere. And spheres are just Q spheres are just Q manifolds for which the Euler characteristic satisfies the Euler-Gem formula. So these are generalized spheres, and Dehn-Sommerville manifolds are generalized manifolds. They carry all the properties of manifolds, and one of the points which I wanted to make, which is new, is that the level sets of a Dehn-Sommerville manifold is again a Dehn-Sommerville manifold. One can also look at everything we have done before, like what happens is odd-dimensional Dehn-Sommerville manifolds are always Dehn-Sommerville spheres because the Euler characteristic is 0. One can see this with the sphere formula, beautiful formula, which is that the sum of the Euler characteristics of spheres around odd-dimensional simplices is the sum of the Euler characteristic of spheres of even-dimensional simplices. Then we have curvature. That's the discrete analog of the Gauss-Bonnet Chern curvature, but works also in odd dimensions. And actually every simplicial complex, that's true. This Gauss-Bonnet formula is true for every simplicial complex. But in order to see what I saw very early on in 2010, 2011, that odd dimensional manifolds are flat with respect to this metric. So I wanted to prove this. I could eventually prove this using Poincare-Hopf, using index expectation. You can see curvature as an expectation of indices. And then there is this symmetric index, which I'm very fond of, because what it is the Euler characteristic of the level surface of a unit sphere. So it's a codimension 2 manifold Euler characteristic. And in odd dimensional manifolds, it's of course 0, because odd dimensional manifolds have 0. So using this level set construction, we see that these center manifolds have also 0 Euler characteristics, so that these indices are 0, the expectation is 0, so curvature is 0. Now one can see also this whole story in the context of valuations. That's how I got in independently again. One can see one has a Q plus 1 dimensional space of valuations, and the bases are the coefficients of the F vector, and so we can write special valuations. This is the traditional way how Dehn-Sommerville invariants have been introduced. What is my contribution here to see that every valuation has a Gauss-Bonnet formula, and then see that these valuations here have the property that the curvature is the valuations for Q minus 1, K minus 1, just one lower. And so this gives just a Q half dimensional invariant set. So, and we can see this invariance, this Dehn-Sommerville invariance, also as using eigenfunctions of the Barycentric refinement operator transpose. So that's another story, and they are related. So these are the same spaces, just different bases for the different spaces. Now, also that's kind of something which makes the whole story much more elegant, is that you can write everything using simplex generating functions. So here calculus comes in, and Gauss-Bonnet cannot be more beautiful. Gauss-Bonnet tells you that the derivative of the generating function of G is the sum of the generating functions of the unit spheres. So you can also integrate that, and you can see that properties from unit spheres go over to the space itself. Now that's another thing which makes things very elegant. You don't need this mess here. What you can define is from the simplex generating function you can define another function which then is palindromic, meaning that the coefficients are palindromic. So there are again half of the coefficients fk are redundant in a manifold. That's like in Poincare duality, where half of the coefficients are redundant. However, Poincare duality does not hold in this, general space. So it's a different story, but it's in spirit similar, that we have symmetries in this space. Also, what is nice is like the sphere monoid, spheres form a monoid, right? Using the join, we have that also for these Dehn-Sommerville spheres. Every odd-dimensional manifold is a Dehn-Sommerville sphere. So we have a monoid of odd-dimensional manifolds, for example, which is nice. And so they have edge refinement, barycentric refinement, soft barycentric refinement. It's connected some, all the constructions for manifolds also hold for this Dehn-Sommerville manifolds. The level sets I mentioned, and one of the things which I wonder is whether there is some relevance in physics. What can happen in these Dehn-Sommerville manifolds is that there are places where the unit spheres are not usual spheres. So these are kind of like singularities. For example, we can build we can take a three-dimensional manifold, Dehn-Sommerville manifold, where some unit spheres are disjoint unions of projective planes, because they have order characteristic 1, so this is satisfied as a unit sphere. This is possible, but this remains to be seen. The cohomology is very similar, but the quadratic homology is very different. There can be kind of much richer structure of quadratic cohomology, interaction cohomology. You see, these manifolds can come together like that, and kind of at a point, for example, and the usual cohomology is not that interesting, but the quadratic cohomology can be very interesting at such points, because you have interactions of higher dimensional spaces which come together at some point. There are interesting things still to be explored, but that's it for today.